All right, thanks, Kristen. So this is our next version of the webinar series that we started maybe half a year ago. So the format is as a reminder to have a 30-minute session, about 15 minutes of a talk and 15 minutes Q&A. So the aim is to learn more about the different work that we're doing as a science team on salt related issues in terms of the overturning circulation. We're looking for volunteers for upcoming webinars, so please let us know if you're interested. So today's talk will be given by Wei Liu, and the title of his talk is going to be Rethinking the AMOC Stability in Climate Models. Wei Liu had received his PhD at the University of Wisconsin in 2012 with Zhengyu Liu. Then he was a postdoc at Scripps for 3 years. But currently he's a postdoctoral research associate at Yale University. And I'm looking forward to your presentation, Wei, so please go ahead.
Thank you very much. Thank you, so thank you, Robert. Thank you, everyone. And so I'm Wei Liu. Today I will talk about work from my PhD study and also my postdoc study, focusing on the stability of Atlantic meridional overturning circulation, so in climate models. So this study, the background is we know that abrupt cloud AMOC can cause abrupt climate change. So this climate change of AMOC is usually considered to be associated with the multiple equilibrium of the circulation. So, but the problem is that in current climate models, the model can only simulate AMOC with single equilibrium. So that's a problem. And here I give two examples. One example is in the paleoclimate simulation. So if we want to get a collapsed AMOC, like during the Henry-1 event, we need to put a strong and long-lasting freshwater in the model, say in the NCAR-CCSMC model. So this work has been shown. And the other example is that in lots of climate models, when we do the post-like 100-year but very strong freshwater hosting experiment, we will see that the AMOC will recover rapidly after we remove the hosting mostly. So those two examples show that the current climate models simulate the AMOC is too stable. And also in the simplified model simulations, in the future projection, this could be related because all the models show that the AMOC only moderately weakened, but not collapsed in the next few centuries. So that's the motivation for me to conduct this study. So the scientific questions is three questions. First, whether we can get an indicator to monitor the AMOC stability in fully coupled climate models. Then, based on this indicator, whether we can get some reason, why the most climate models fail to obtain the AMOC with multiple equilibrium. And at last, we want to know whether this stability bias of AMOC will affect model future projection. So first, let's go to the indicator. And the original idea of the indicator came from simple box model. Here I show the Rumsdorf box model. Basically, you can see there is like a 4 box sinking in the north, and at the south, it's kind of open boundary around 34 south degree. It's boundary between South Atlantic and the Southern Ocean. So Rumsdorf box model shows that the freshwater flux F1, you can see it here, is downstream of the sinking region. Is regarded as the indicator. So when F1 is bigger than 0, here, not here, F1 is salinity faulting. When F1 is bigger than 0, it's can is correspond to the multiple equilibrium of the AMOC, and so the other sign is the same. Okay, so this is the box model, and how can we get the climate model version of this indicator? And so on the right, it shows that in climate models, people will use freshwater budget analysis and determine that the, around 34 South degree, the freshwater transport is used as an indicator to monitor the AMOC stability. And people will think when the, this indicator is negative, means a freshwater export, which indicates AMOC in a multiple equilibrium. So how can we understand? So how can we understand this mechanism? And so we can see that when this indicator is positive, which means the AMOC will import fresh water into the Atlantic basin. So when the AMOC collapses, and this fresh water imports will also disappear, which will cause salinity accumulated in the Atlantic basin, which will help the AMOC to recover. On the other side, if for an active AMOC, it exports fresh water out of the basin. When the circulation collapses, the fresh water will accumulate in the basin, which will make the AMOC enter a collapse state and will not recover. So does this indicator work? It may not work. Here I show two examples. Basically, it's two models. So in the left is the AMOC, and so it's from the paper by Beers and Weber, 2005. So they tuned this model into different states, and for the states C and D, you can see the red and the black state. The indicator is negative, means freshwater export. So if we base on this indicator, so the AMOC should be in a multiple equilibrium, and so when you do the housing, like here, around 100 years, and remove the housing, the AMOC will keep collapse. But here we can see that this is not the case, and the AMOC recovers when the housing removed. Also, I did a similar thing, but I please focus on the NCACSM3 control, PD control run. So for the PD control run, the indicator also negative, but when I do the housing, pulse-like, and the AMOC also recovers. So this means this indicator may not work. Then we will think whether we can find an alternative indicator. And there's some early try from Digestra 2007 paper. And so he includes the northern boundary. So here we are not only focused on the southern boundary, but we focus both south and north. We are focusing on the freshwater divergence in the Atlantic basin. And the southern boundary he chose is 60 north degree. And so my work is I further refine this indicator. I choose the southern boundary as 80 degree. The reason is that 80 degree is the boundary between the Atlantic, North Atlantic, and Arctic. So you can see the freshwater exchange between these two basins across three channels, the Frame Strait and the west shelf of Bering Sea, and also Canadian Arctic archipelago. So through these three channels, freshwater will exchange and between the two basins and will affect the deep water formation in the Jane Seas and Labrador Seas and then the AMOC. So then I defined this indicator. So the indicator shows that when it's negative, which means a freshwater divergence across the Atlantic basin, which means the AMOC in a multi-equilibrium region. So now we have the indicator, and we can focus on the inconsistency, climate models, and observations. So here I show that the observations, when you calculate the indicator, it shows its negative value, which means if we follow observations, current AMOC is in a multiple equilibrium region. However, in climate models, and this value is positive, it shows a different region. And we can see that why the different, the northern boundary is mostly the same. The reason is because of the southern boundary. And in the climate models, the upper ocean of the southern boundary is too fresh, and we think it's probably related to the WITCD issue. And so that's the reason why the model has this AMOC stability bias. So then I continue this work, and I think whether we can correct this bias, and then we check how the stability looks like. So I focus on the Inconsistency. So I want to correct the salinity bias in this model, and further to correct the AMOC stability bias to make the model be consistent with observation. So here is the left show that using the flux adjustment method, I correct the bias. The left is temperature, the right is salinity. Basically, you can see globally it's much more reduced. And at the southern boundary, you can see the control run is the blue curve here, and the red line is the corrected version. This silver color is the observation, and this gray shading is simplified model. So you can see that when I do the correction, and it will correct the stratification at the southern boundary. Furthermore, it will correct the indicator to be consistent with observation with a negative value. So this is the control run, this is the corrected run. Oops. Now I have already corrected the AMOC stability from the indicator view, and then I want to do the test. So basically, I do the one thread drop 100-year pulse-like freshwater hosting experiment. So the top panel is the CCSM3 control run. You can see the AMOC recovers because it's in a single equilibrium region. But when I do the correction, make it consistent with the observation, now the AMOC is in a multiple equilibrium region. When I do the pulse-like hosting, so even I remove the hosting, the AMOC still keep collapse after the next 1,000 years. So then I enter the last question. So whether this AMOC stability bias will affect our future projection. On the top panel, it shows that simplified models basically only show a moderate about 1/4 decrease of the AMOC strength in the RCP 45 scenario. So the bottom, I show that, so the blue line is the control run. Basically, you can see it's around 15 thread drop. The blue is the control run, and the red is corrected run. So when I do the double CO2 experiment to mimic the global warming future, so we can see that when for the control run, the AMOC collapsed a little bit, and then recover a little bit around, I think it's only reduced about 1/4. But when I do the double CO2 to the corrected version, now the AMOC rapidly collapsed, and then after like 300 years, and keep collected after all. So the reason is that we can see basically when the AMOC have different stability, it will have different feedback process. So here I show the freshwater transport in this global warming experiments in two different versions. So here you can see the red is the freshwater convergence, and in the correct version, and this is the control run. So you can see that due to this different biostability, and the AMOC will have different response in global warming experiments. So due to the different changes of the AMOC, it will have different global responses. So the left panel shows the responses of surface temperature, and the right panel shows the precipitation. So we can see that due to the collapse of the AMOC, and it will have a large cooling hole in the North Atlantic region, and also it will shift the ITCD to the southward, especially in the Atlantic part. So finally, I want to stress that this global warming experiment and the hosting experiment are quite different. The difference in two aspects. First, in the global warming experiment, WCO2, you can see the AMOC collapse is primarily due to the thermal flux change. So hosting, because we add fresh water, it's due to the highland part. Also, we will see that, and the magnitude is different. Here probably you cannot see quite well, but I can tell you the hosting magnitude is much larger. It should be 1 order larger than the WCO2 forcing. So which means the future climate, we may only have a moderate freshwater. We may only have a moderate buoyancy flux change, and so this scenario is different from the hosting scenario. So here I give the conclusion. So first, I define a diagnostic indicator for the AMOC stability, and based on this indicator, we can show that the current climate models have a bias in the AMOC stability due to the freshwater bias in the southern boundary. And so if we correct this bias, and we will have a quite different scenario for future projection. So after all, the flux adjustment is a first aid method. It's not ideally approach to fix this problem. So how can we solve this problem using some physically improved model? I think we may have 2 ways. First, we may want to address the double ITCD issue, and second, maybe we can go to the high resolution model, such as the angular leakage. If it's improved, it will improve the stratification at the southern boundary, and then it can be improve this bias issue. And okay, thank you very much.
The conference has been unmuted.
Thank you for that excellent presentation. I just took everyone off mute so that we can ask questions pretty freely. I do see a few hands that have gone up, so why don't I start calling on people? And if you have a question, go ahead and raise your hand so I can get you queued up. Gokhan, go ahead. I saw you first.
Yeah, I thank you for the presentation, and it's in the conclusion slide that you have it to number 2 bullet. You say observations suggest that modern AMOC is in a ME regime. I didn't see any observations from your presentation. You were essentially talking about the reanalysis products, and they are not observations. We had a sense, we know that the reanalysis products have all kinds of biases, and especially at depth, they do not really represent anything meaningful. Do you have any actual real observations, and what's your take on the other reanalysis products? Because they were not agreeing among each other either.
Okay, thank you very much. And I think, this is a question about real analysis data. Means you mentioned it's not the real observation. So here I give the results for the real analysis data because it contains both temperature and observation, both temperature and velocity observations, like a global grid product. But I do have examined the real observations from the Argo SBT or CTD, and I collect the data observations from previous literatures. So at the southern boundary, the range is between minus 0.34 to minus 0.13 drop through all these data sources. And at the northern boundary, it's I think etc. 2006 have a review paper and to talk about this freshwater transport through these three channels. And the total number is about 0.189 drop. But look here is the total. It contains the gyre part and also the overturning part. So the overturning part is about 1.6 or 1.5 something. So if we add them two together, and we will get the value is about the net, the convergence or divergence, the net value is about minus 0.18 to positive 0.6. So there's still a large chance for the AMOC in ME regime, but I should say there are lots of uncertainty in these observations. It's a huge range.
Gokhan, do you have a follow-up?
Yeah, that's fine. I mean, another approach might be we have lots of core simulations, forced ocean simulations. It will be interesting to see whether they actually show something like this or not, and how dependent it is to the surface salinity restoring.
Yes, that's a good point. And so here I do this thing in a fully coupled version. And so you may notice that I did both temperature restoring and salinity restoring. The reason is that I did do the salinity restoring only, but because the temperature bias is very big in the North Atlantic, you will see there are huge bias there. So if I only restore the salinity, so the AMOC will get huge and until the model blew up. So I have to restore both temperature and salinity to make the AMOC strength with a reasonable value. And also the reason I do this work in a coupled scenario is because I create this bias in a coupled system. So then I will get the fully response from the atmosphere or other components when the AMOC have a huge change like this way. So then I can compare. And another thing is that I studied parallelly, built two versions. And you may see that for the correct version and the control version, the only difference is because of AMOC stability difference. And the other physical process is the same. So by comparing these two version experiments, and I can draw the conclusion, this change is due to the AMOC stability change, not from other thing else.
Okay, and we also, Paula, you had a question?
Yeah, I just had so the flux correction went by a little bit quickly. Could you show again what you did to correct exactly? So I noticed that it was a restoring, but it wasn't everywhere, right? It was only in certain places. And what were the time scales?
I kind of go too quick because of time.
There it is. Okay, so So what were the time scales, please, for the heat flux and for the salinity?
Oh, okay. So this part is I two steps. First, I do the restoring, and I give it's globally both temperature and the salinity. So I give the restoring like the 10 days. It's kind of
for both temperature and salinity.
Right.
Both.
Because
so they're the same.
Both. Yeah, they are the same. Because I want to quickly drag the temperature and salinity into observation. And so I run that for 1,000 years, and so make it kind of quasi equilibrium. Then I took the last 100 years average climatology. So that one is I use that as a flux adjustment for this two flux, the freshwater and heat flux. So I pull that and into the model again, and to run a model for a couple. For another 800 years, couple hundred years. Then at last, I will build a corrective version using this method.
Sorry, say this again. And then in the last, what did you do in the last years? Didn't hear.
Oh,
you.
So after I get the restoring, I ran the model for 1,000 years, and I took the last 100 year average, the heat flux and the freshwater flux as a part I needed to adjust it. So I added this part into the model, and make the model running continually again. And so this time I get the flux adjusted version of the control run.
Thanks. And Zoli, go ahead.
Yes, hello. I quite liked the plot that you showed at the beginning that showed the cross-section from the southern hemisphere to the northern hemisphere, because that made it clear that you did need a northern boundary for doing the difference in MOV. But it seems like something else that is missing, and the discussion we've been, questions that Paola and Gohan asked get to this also, is that you're assuming that there's nothing happening in the ocean between 35 south and 60 north, but we know that there's connection with the atmosphere. And it's based on what you've been presenting, that knowing the atmospheric input between 35 south and 60 north is essential for the stability of AMOC. Do you have any thoughts on how you might look at that?
Oh, okay. So yeah, I cannot hear very clearly, but if I repeat the question, so you are asking about the northern boundary difference. Why choose the 80 north degree instead of the 50 north degree? And so you also mentioned about the air-sea interactions, most important between 35 north and 50 north. Is that right?
I guess more or less. I guess you bound the south and the north, but you don't have a flux at the surface, and that seems like that's what's missing to bound the volume that is the ocean.
Okay. Yeah. So here, so the Pediatra 2007 paper choose the 50 north degree, and here I choose the 80 north. So the reason is that since the AMOC, the deep water formation for the AMOC, the deep water formation in the two regions, and besides the Labrador Sea, is also in the Jane Seas, and so I think it's good to cover the Jane Seas. It's because even you have the big change in the Labrador Sea, but the freshwater transport between the Jane Sea and Labrador Sea is very important. And there are lots of feedbacks, like the freshwater outflow and also the sea ice transport, and lots of things can affect the change of the AMOC. So that's to say, it would be desirable to consider the freshwater transport in the Jane Sea area. So that's the reason I choose the boundary here. And also, I want to emphasize that. And so this freshwater transport as an indicator basically is directly related to the AMOC strength. So you may notice that this one is the property of the AMOC itself, and the atmosphere will respond to the AMOC change, but the atmosphere definitely is not the thing to determine whether this indicator is positive or negative.
Okay, that makes sense, and I agree with you. Could I rephrase my question a little bit more clearly, perhaps?
Hello. Yeah.
Yeah, I guess that all makes sense. I guess what I'm saying, if you look in the box model on the top left of the screen now, I'm saying there's fluxes into that upper box from the atmosphere, and I guess I know, it seems like those have an impact on the stability also, and it's not just the oceanic transport. But anyway, it's not really a question, so you've answered my question. Thank you very much.
Thank you.
Okay, let's do one more question, and then maybe we'll get wrapped up for the day. Steve, go ahead.
Yeah, thanks, Wei Liu, for that talk. It was very interesting. So my question is just a clarification question, because you went by quite quickly. When you're doing your restoring experiments, it looked to me like most of the model bias was in the subpolar gyre of the Atlantic. There wasn't very large biases in the South Atlantic, or at least not as large as in the North Atlantic. And so my question is, how did you identify the MOVS as the source of the stability bias in the models? Can you go over that again?
Oh, thank you very much. Yeah, this is really good question, and so you can see that the bias is large in the North Atlantic, and for the South Atlantic it's relatively small, and so yeah, and I think this bias is related to the both the ocean circulation and also from the precipitation from the atmosphere. And it would be a clear version if I only restore the salinity as a southern boundary. I think I did one part. I did the experiment in my 2014 paper, and so if I only do the regional flux correction, and it will affect it will improve the salinity bias at the southern boundary, and also kind of drag the indicator towards observation. But that is not enough, and I show in my paper, and it's not it's still a little bit away from the observation, and so I think both to the south is definitely important, and for the north, and I'm not quite sure about this part. It's because you can see here from this profile, the temperature, the salinity profile. If I do the correction, for the south, it's okay in the upper 400 meters because of the subduction or surface process is okay. But for the deep water, because we know that North Atlantic deep water came from the north, and this part is still, is not good, and I think that part is also related to probably the mixing, the mixing in the model. So I think it's a complex issue, and I should say it's mainly from the south, but from the north, we have no clue yet how this will affect this stratification. And there are lots of like mixing or the other issue maybe get involved.
Yeah, well, I guess, a related question is in that lower right panel, you're showing that MOVN from the models is agreeing with your observational estimates, even though the models are highly biased in the north.
Okay. So, yes. Yeah, so you see here, right? So even I do the flux correction, there's still some bias in the north. So this is your question?
I think Steve is referring to the lower right panel.
Lower right panel, panel B there.
Panel B. Oh, okay. The north here is here the control line is the black dot, and the other colors are the real analysis. So the corrected is red, and the red one I think is very close to the others real analysis data. And so I think from the nose, it has some small change, but generally the sign is okay, it's negative, and the magnitude is very close. And so here we can see the only difference between the models and the observations came from the source. You can see the models, the simplified models, the gray here, and also the blue dots, the CCSM3, show it's like close to 0 or maybe positive. And for the observation, it's definitely negative, means freshwater export. So combine these two, we will see the difference then for the delta MOV in these two categories.
Okay, thank you.
Thank you.
Thank you, Wei, and thanks everyone for the questions.